In the last video, we ended with this gate set, C0, Hadamard, and this phase gate. And remember, the phase gate was one that added a relative phase. The Hadamard, you recall, is the one that takes the 0 state to the plus state, and the C0 was our controlled NOT gate, which flipped the second qubit if the first qubit was in the 1 state. So this generates entanglement. Remember, with the Hadamard and the C0, we can generate a nice entangled state. However, with Hadamards and C0s, we don't seem to be able to capture any complex numbers. The relative phase gate here gives us those complex numbers, so perhaps we're kind of covering all of the interesting things in quantum computation with these three gates. The issue is that there's a classical efficient simulation for circuits that are built up of these gates. And the way in which it's done is through a clever kind of mathematical trick for representing information that is beyond kind of the scope of these lectures. But the important thing is that there's just one extra gate called the T gate, which promotes this gate set to universal quantum computation. So that can also be proven that with just this extra T gate, now I can perform any unitary that I like on any number of qubits. So just a schematic of what that means. I have a large quantum algorithm. Is just one big unitary that acts on n qubits. So that's a 2 to the n by 2 to the n matrix. And what we're saying is that with just these single qubit gates and the C0 gate, I can find some way to compile that algorithm down into one that just uses these 4 gates. And the length of the circuit depends only on how close you want to get to the target. Now, the space of unitaries is a continuous infinity, so clearly I can't get to any particular unitary precisely. However, the result of the Solovay-Kitaev theorem that we talked about in the very first lecture showed that you can get arbitrarily close with a gate length of your algorithm that grows only logarithmically. So with very little overhead, I can get closer and closer to the target gate. So that's great. And the important thing here is that I only need a single 2-qubit gate and 3 single qubit gates. And I don't need any more complicated gates than that. The interesting thing about this T gate is its form kind of suggests that it may only crop up in the kind of peculiar situations. However, I want to show you that in quite a sort of simple, in some sense, very classical quantum computation, the T gate actually shows up quite prominently. So this is your first quantum primitive. So we had these 1 and 2 qubit gates. Now we're going to introduce your first 3 qubit gate, and it's not too difficult. It looks just like a C0 because it's also called the CC0, the control knot. And how it works is if the first 2 qubits are 1, then it flips the last qubit. So just like a C0, if the first qubit is 1, it flips the second qubit. If it's 0, it doesn't do anything. So this one is only if the first 2 qubits are 1, the second one, the third one in this case, is flipped. So that's an 8 by 8 matrix. I don't want to write it down. It only has 8 non-zero entries in it, but it looks just like pretty much like a C0 gate. it's better, I think, to write it down. Yeah, okay, fine. Yeah, let's write it down. Well, we'll have to make sure of that. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6. And what it looks like is this NOT gate at the bottom. Maybe I should have written it down. And then it's zeros everywhere else. Okay. What it's saying is that a CC NOT takes any basis vector and produces another basis vector. In this case, one that, so the last qubit is in the state C or A end. Right? And it's related to the NAND gate because this thing here, say if C is 1, adding modulus 2, A and B is just negating A and B, so that's not A and B. So we can use this notation. Right, so that's not A and B, that's the NAND gate. This also shows that embedded within classical quantum computation is classical computation. So the NAND gate is universal for classical digital logic. So any logic circuit that I want to run on bits can be written as just a sequence of NAND gates, and for every NAND gate I can do it reversibly with this Toffoli gate. So within quantum computation I can do classical computation. So that already shows that quantum computation contains classical computation. Now this is a 3-qubit gate. It's not in our gate set, and was promised that we can get as close as we like to this gate using a sequence of gates from this 4-gate set. In this case, we can get precisely there, so we can actually implement this Toffoli gate exactly with the gate set above. And this is where these T gates come in. So this is equal to the following. It's a bit of a mess. Let me get it right. Make sure I have enough room here. Hadamard. C naught. T inverse. C naught. T. C naught gate. T inverse. C naught, 2 T gates. Another Hadamard. Another C naught. That's going to be here. Wow. There it is. So the thing on the left is this Toffoli gate, this classical NAND gate, which you might think is a seemingly simple gate. And the thing on the right is its decomposition in the 1 and 2 qubit gates from the gate set that we had above. Now, that's not a unique way to write it down, but it's interesting that these thing on the left, which just maps basis states to other basis states, now contains these T gates, which contain these complex numbers. So above, no complex numbers at all appear in the Toffoli gate, but below, you seem to be have complex numbers at least cropping up within the decomposition in 1 and 2 qubit gates. We can look at this with our simulator. So here I have again the Quirk simulator. You can see the web address there, and we can try to implement and double check whether or not this decomposition, this quantum circuit, is actually implementing the gate promised above. So we can put all of our gates down one at a time. The nice thing about Quirk is it implements the inverse of the T gate for us. T. 2 more T gates. Analog gates. There we go. So we started the computation in the all zero state, and we end in the all zero state. That's what the Toffoli gate is meant to do, because the first 2 qubits are 0, so the second or the last qubit has to be 0. We can flip these qubits by putting a NOT gate at the beginning. So let's make the first qubit 1. And we see that the amplitude is now changed, so that the first qubit is now in the 1 state. But nothing has changed to the second or the third, because that's what the Toffoli gate is meant to do. We can move that NOT gate to the second one and see now that the second qubit is in the 1 state at the beginning and at the end, as promised. And if we put 2 NOT gates, so the first 2 qubits are 1, 1, then that final qubit should be flipped, and we see at the end that the coefficient in front of the 1, 1, 1 state is 1, and we have 0 everywhere else. So, well, there's to check to see whether or not to find out what a 3-qubit unitary does, you have to check all 8 basis states. In this case, I've showed you 4, so as this homework you can do the other 4, but you can also believe me that this is how it works. So it still doesn't tell us, so this kind of convinces us that this is indeed the decomposition or a decomposition of the Toffoli gate into 1 and 2 qubit gates, in particular ones from that gate set above. But why do you have these T gates here? These are things that produce these relative phases, and in particular the pi over 4 phase that's coming up. And the reason is we can see by looking at this gate here. So let's look at this one here. So here's a circuit. It has a new gate. It's a controlled gate. So just like a controlled NOT, you can have a controlled unitary. So if the control is 1, the unitary is enacted on the other qubit. If the control is 0, then nothing happens. And the gate we're going to stick in there is the square root of x. And although x is quite simple, as you recall, the x gate is 0, 1, 1, 0, and the x over the square root of x gate is something that looks significantly more complicated. Although it's obviously still a 2x2 matrix. Okay, so the point is, now you can check this on your own. If you square, sorry, x to the 1/2, if you square that, you get an x gate. Okay, that's believable. But what does that have to do with the Toffoli gate? Well, let's have a look. If we start with 0, 0, 0, then yeah, I have two controls, and the controls don't do anything, so I end in 0, 0, 0. Now, let's start in 1, 0, 0. If I start in 1 at the top qubit, then after the first gate here, I have 0, 0. But after the second gate, I have a C naught, so the control is in 1, so now that second qubit flips to 1, and when I get to this third gate, what happens is there's an x to the minus 1/2, an inverse of the square root of x gate, being applied to the third qubit. Okay, so this is still in the 1 state, this is still in the 1 state, and now down here I have an x to the minus 1/2 being applied to 0. The control in the first qubit is 1, so that means I flip this back to 0, and the control is still in 1 up here. The second one is 0. Now I apply an x to the 1/2 to what was already there, x to the minus 1/2 on 0, and these two things are inverses of each other, so that's the identity, and well, I end up in 1, 0, 0, which is where I started, which is what the Toffoli gate is meant to do. Okay. And we could have done a similar thing with the 0, 1, 0, but that's not the interesting case. The interesting case is when we have a 1, 1. So the Toffoli is meant to perform an X gate on the final qubit, and the original two qubits are meant to stay in the 1 state. So after this point here, this control is in 1, and I've applied an x to the 1/2. The first qubit is in 1, so now the second qubit flips to 0, in which case this x to the minus 1/2, the inverse of the square root of x, does not get applied. So nothing happens. I remain at this point I remain in x to the 1/2 at the bottom. The control up at the top stays in 1 the whole time, so that flips back to 1, and the final gate does get controlled, so that another x to the 1/2 is applied to the final one, and well, I have x to the 1/2, x to the 1/2, I said the definition of it, x to the 1/2 is that it squares to the x gate, so that actually flips it, and this qubit was in 1, this qubit was in 1, so there we go. So by the difficult thing when we decompose these is not necessarily like how we're going to perform these controlled operations, but we actually have to get back to where we started with these control bits. So the first one, you can see it flipped from 1 to 0, but then it had to flip back from 0 to 1. So you have to do this kind of reverse thing, which we'll see much later on in the subject. So one thing you can do is convince yourself that this construction actually is more general, and you can do this with other controlled unitaries. So not just control knots, but other more complicated primitives that might look like lots of controls and maybe some unitary at the end. And you can do a similar thing to what's happening here. So it's a good exercise to try to come up with a similar way to decompose this multi-qubit gate into 1 and 2 qubit gates. And if you're brave enough, you can start to play with trying to get things into decompositions which use only this gate step here. I recommend you play around with tools such as Quirk to get a feel for how these things work. And remember that when you're analyzing these circuits, you just step through one time step at a time. Time flows from left to right. So after each gate, I can update all of the states. In this case here, we've seen that it's quite easy because we haven't had to deal with superposition. So in the tutorial, we will see how we can analyze these circuits when there's superpositions. That's all.